So good evening, everyone. Am I audible? And are you able to see my screen?
Yes, sir. Good evening, sir.
Good evening,
You are
sir.
audible.
Okay. My screen is visible to you?
Yes, sir. Yes, sir. Visible, sir.
Okay. So,
Recording in progress.
yeah, so we'll continue where we left last class. Just to have a brief recap, this is the second order system that we were talking about. Typically, you have an output for a given input. And this is the transfer function, okay? And you first define the poles of the system by equating the denominator here to 0. So you basically have two different poles, how you get the roots of this quadratic equation. So one will be minus omega n xi plus omega n square root of xi square minus 1. And the other one will be minus omega n xi minus omega n into square root of xi square minus 1. So, and depending on the value of xi, we look at different kinds of systems. If xi is greater than 1, the damping coefficient is greater than 1, from these expressions, you can see that when xi is greater than 1, square root of xi square minus 1 is going to be real. That means both these roots are going to be real. So the poles are going to be real. So you can see that in the response plot, you have the real axis here, sigma, and this is the imaginary axis. So for a overdamped system, when xi greater than 1, both the roots of this equation or the poles are going to lie in the negative real axis. When it is minus omega n xi plus omega n, that will be this pole here. And then when it is minus omega n xi minus omega n into xi square minus 1, that will be this pole here. Now, when you talk about an undamped case, that means there is no damping. So basically, your xi becomes 0. So this term vanishes. And when xi becomes 0, you are basically talking about square root of minus 1. So that will be I into or j into omega n. So you have basically plus omega n minus omega n. So it will be plus j omega n and minus j omega n. Depending on that, you will have one complex pole here and one complex pole in the negative complex region. When you have a critically damped system, for a critically damped system, your xi is equal to 1. So when xi becomes equal to 1, basically this entire term here becomes 0. So you have basically minus omega n xi here and minus omega n xi here. So that means both the poles would coincide here, and it will be on the negative real axis. And finally, we talked about some of the response of an underdamped system. So for an underdamped system, as we said, the xi is going to be between 0 to 1. And omega n is greater than 0. So this is a typical response. So x-axis you have time, y-axis you have the output. So you subject the system to step input here, unit step input. This is basically the input. And the output basically varies from 0. And this is where it overshoots the input and oscillates around the output and finally becomes exactly equal to the output. So this is the type of response typically you would see for an underdamped system when xi is 0 to 1. So we talk about various different characteristics, delay time, rise time, peak time, maximum overshoot, and settling time. So these characteristics we are going to look at because these are very important for a second order system. Now, first we talk about the delay time. So if you see the response, the output basically increases to follow the input. And this is where it first time crosses the input, overshoots and then oscillates. So delay time is basically the time that is required for the response to reach half the final value the very first time. Okay, so this is where the output reaches the input the very first time. And if you take this as the time and half of it, right? So, sorry, so this is the final value, which is 1. So the half is basically here. And the corresponding time required to reach the half of the maximum, the final value. This time is known as the delay time, TD. Then we talk about rise time. Rise time is the time that is required for the response to rise from either 10% to 9%, 90%, or 5% to 95%, or 0% to 100%. There are 3 different ways you can define the rise time. So, and for an underdamped second-order system, typically you use 0% to 100% rise time. And for an overdamped system, you typically use from 10% to 90% rise time. Now you can see here, this is basically the time required for a underdamped system, 0% to 100%. So 0 is here, 100 is here. So this is basically the time it takes to go from 0 to 100%. Then we talk about peak time. Peak time is basically the time required for the response to reach the first peak of the overshoot. Okay. So it starts from 0, as I said, it goes and shoots over the input, reaches the peak, and then comes down and oscillates. So it is basically the time here where the first peak after the overshoot is reached, right? So going from 0, crossing over 1 and going to the peak, this time is known as the peak time. Then we talk about the maximum overshoot. The maximum overshoot is the maximum peak value of the response curve measured from unity. That means if this is the unity input, the input is 1. This is basically the maximum overshoot. And if the final steady state value of the response differs from unity, if let's say the steady state value is not unity, some other value, let's say call it at C at T equal to infinity, then we can define the maximum overshoot in terms of percentage. So we say that maximum percentage overshoot is the value of the output at the peak time. That means when T equal to T peak, what is the value of the output? Minus the value of the output when T tends to infinity, that is the steady state value, divided by the steady state value into 100. Okay. So this is how you define the maximum overshoot when the input is not unity. Okay. And this maximum overshoot basically representative of the stability of the system. If overshoot is minimum, then the system tends to be more stable than is a case where overshoot is very high. Typically, in some situations, the overshoot can destabilize the system, and system can never return to its original steady state value. So that is why this overshoot is used to characterize the stability of systems. Finally, we talk about settling time. So how do you define settling time? The settling time is the time that is required for the response curve to reach and stay within a range of final value, which is about plus minus 2% to 5% of the final steady state value. That means here the final steady state value is 1. And we know that the response would basically overshoot and oscillate. Now, at some point, these oscillations are going to be within plus minus 2% to 5% of the steady state value. And when that is reached, you talk about the settling time. That means you can see that here it has overshoot and here it has come down, and these values are actually greater than 5%. Now you can see that in this cycle here, this deviation from the steady state value is less than 5%. And starting from here, it is actually less than 5%. So basically, this time from t equal to 0 to the time where the deviations are less than 5% is known as settling time. So you now have not only a characteristic underdamped system, but you have these parameters to characterize a typical underdamped system. Okay. Now, we talk about the response of a typical...
Sir, I'm sorry. Can you just repeat about the settling time concept, sir? I could not follow it properly.
Yeah. So the response basically increases, right, from 0 finally to reach a steady state value, the input. But in doing so, for an underdamped system, it actually overshoots the steady state value, then oscillates around the steady state value. Now, 1 is the steady state value. If you draw these horizontal lines, which is about plus minus 5% of the steady state value, that means if the steady state value is 1, you say that 1 plus 0.05 and 1 minus 0.05. And this response, when it overshoots and deviates from the steady state value, when it is coming within that 5%, that means within 0.05, that time is known as the settling time. Because after that, never the deviations are going to be more than 0.05 or 5% of the steady state value. Always after that, it is going to be less than 5% of the steady state value. So the first time, the time after which the output never exceeds 5% of the steady state value is known as the settling time. Okay.
Thank you, sir. Thank you so much. Yeah, it's clear now.
Now, we talk about step response of an underdamped system, similar to how we did for a first order system. In a second order system, for an underdamped system, we talk about if the input happens to be a step input, your RS happens to be a step input, how the response is going to look like. So you have a typical transfer function which relates the output with input. And in this particular case, when you talk about a step input and you are talking about a frequency domain, and you know that the input is not in the time domain, it is in the frequency domain. And for for an input of 1 in the time domain, in the frequency domain, the expression becomes 1 over S, right? If you remember when we talked about the Laplace transformation, when we take a Laplace transformation of a unit function, the value is 1, you get in the frequency domain, you get as 1 over S. So basically, and this is the transfer function. So your output for a step input is going to be 1 over S times the transfer function. So this is basically going to be the output for a unit step input. Now this you may not be able to appreciate because you do not have an inverse Laplace transformation of this entire term. So you do some algebraic modification. And this term you can actually write the difference of two different terms. So you can write as 1 over S minus s plus 2 j omega n divided by s square plus 2 j omega n s plus omega n square. So basically, if you do the math here, you can go back here, but now you have expressed the single term as two different terms. Now you do further modification. You write this as 1 over s minus, this is s plus 2 j omega n. The denominator, now you write s square plus 2 j omega n s. Then you want to do this as like a plus b whole square. So you have a square plus 2 into a into b. So the b is basically like j omega n. So you add j square omega n square and subtract j square omega n square, and this omega n square is simply brought here. Okay, so we basically in the denominator you add j square omega n square and you subtract j square omega n square. Now this can be further written as 1 over s minus s plus 2 j omega n is here. Then this term becomes s plus j omega n whole square. Right? You can see here a square plus b square plus 2ab. Then plus omega n square you take outside of the bracket, and inside the bracket you will have 1 minus j square. Okay. And
sir, I have a question, sir.
yeah.
The second part of the denominator, it looks a bit like the equations we wrote like to the poles of the response. So, I mean, would it be related to it in some way?
Which one? Sorry, this one?
If we go to the last equation.
Yeah. So
because,
you are saying
yes, sir, that one, the two poles what we were talking about.
Yeah. But it has a square root in it. Okay.
Yeah.
So they're not really identical as such. But why we're doing, we'll come to know in a while, because we want to. So basically, when you write from here to here, you still do not have an inverse Laplace, because you want to go from the frequency domain to time domain, right? So you want to have an inverse Laplace. So this you further simplify algebraically. So this is basically the same thing I have written from here. Now you rewrite this as 1 over s minus s plus 2 j omega n, then s plus j omega n whole square, plus what you are saying that this term, now we are calling it as the damped natural frequency of the system. Okay, so if you remember in the very first slide, when I talked about the second order system, I talked about damped natural frequency of the system. Okay, so this is what you are saying, that you are familiar with this expression. So this is basically omega d square, okay, which is the damped natural frequency. Okay, so once you write this, then we still do not have an inverse Laplace of this function. So we again adjust. So you rewrite as 1 over s minus s plus this 2 j omega n you split. Okay. So you write, so there is a minus sign here. So you have minus s plus j omega n and then minus again j omega n. Right. So this 2 j omega n becomes minus j omega n here and minus j omega n there. And the denominator is basically written in both. We have a Laplace inverse of each one of these terms. Okay. So if I, okay, you need still further adjustment, because here you have j omega n and here you have omega d. So you have to make this omega d. So you do that by again writing 1 over s plus this term, same as this term here. But you do some adjustment to this term. That is, you divide 1 minus j square square root and multiply 1 minus j square square root. Then this term becomes omega d now. Okay, so you have 1 over s minus s plus j omega n divided by s plus j omega n whole square plus omega n square minus j over square root 1 minus j square into omega d divided by s plus j omega n whole square plus omega n square. Now we have the Laplace inverse of each one of these terms. So if you want to go from the output from frequency domain to time domain, you can write, so Laplace inverse of 1 over s is basically 1. Okay. And Laplace inverse of this term here is similar to what you see here. So this is from the Laplace table I have reproduced here for your convenience. So if you have a function which is like s minus some constant divided by s minus some constant square plus some other constant square. So this is similar to what you see here, just that your there is a minus sign here, and here it is plus of minus j omega n, right? So this is like s minus minus j omega n divided by s minus j omega n whole square plus omega d whole square. So the inverse Laplace of this function is e to the power at into cosine bt. So the inverse Laplace of this function is going to be e to the power, your a is basically minus j omega n, so that is minus j omega n into t. E to the power at is e to the power minus j omega n into t. Then cosine of bt. So the b is basically omega d, so cosine of omega d into t, right? So you got Laplace inverse of this term. And if you take Laplace inverse of this term, this is a constant, so it will come out. And Laplace inverse of this term is similar to what you see here. So you have b some constant divided by s minus some constant square plus b square. And the Laplace inverse of this is basically e to the power at sine of bt, which is similar to this term here. So you have b as omega d and a as minus j omega n. So you have omega d divided by s minus m square plus omega square. So basically this j divided by 1 minus j square comes, square root comes here. Then this would be e to the power at. So e to the power minus j omega n t. Then sine of bt, sine of omega dt. Right. So this is the solution of the response of a second order system subjected to a step unity input. That means you have a step a function whose value is 1. And this should be the output, the response of a step input for an underdamped system. Now, you can do further math. It's the same thing that I have written here. Now, e to the power minus j omega n t, you can take common. So inside the bracket, you will have cos omega t plus j into square root of 1 minus j square sine omega t. And for an undamped case, when j equal to 0, if you put j equal to 0, then this term is going to go. So you will have basically omega n, your omega d in that case, your omega d will be simply omega n, and which is your undamped frequency. Undamped frequency is basically same as the natural frequency of the system. So in that case, your output will just become 1 minus, so this becomes 1, e to the power 0 becomes 1, this term goes to 0, so it will be simply 1 minus cos omega dt. Now omega d is basically omega n, so omega n into t. Now when you have a when j is non-zero but has a value between 0 to 1, let's say you take a j of 0.1 and omega n as 3, and with these inputs, if you plot, x-axis is your time, y-axis is your response, which is c of time, the ct. So initially, when time t equal to 0, this is 0, right? Because time t equal to 0, this will be 1. And so 1 minus this term will go to this term will go to 0. This is 1. So 1 minus 1 becomes 0. So basically you have 0. And then this is how the response of the system is going to oscillate. oscillate about the unit input. Okay, so it comes like that, overshoots, comes down, then goes smaller and smaller, but keeps on oscillating, and finally it reaches a stable input value. Okay, this is when the damping coefficient is very small. Now, what if you slowly increase the damping? Okay, so when you go to a damping of 0.5, you would see that it will overshoot, but very quickly it is going to reach the steady state input. Okay, that means here the settling time is very, very small. Okay, for a damping of 0.5 compared to that when the damping is small, about 0.1. But when you go a higher damping, something like 0.9, you can see that almost it is behaving like a first order system. Okay, so there is no oscillation in the system. Slowly, gradually, the output basically increases and nicely merges with the input without any oscillation. Okay, this is because your J value is very large. So typically, we can generalize this second order response using this curve that you can see here. Here, this is a three-dimensional plot. This axis is the time axis, omega n into t. And this axis is the J axis, the damping factor. And this axis is the output. Okay. So you can see that for various values of damping factor, the response curve nature is very different. When the damping is very small, you can see that when the damping is 0, this output is basically oscillating about 1. It may never reach the stable steady state value. Okay. And as you provide more and more damping, you can see that the peak overshoot is reducing, and slowly the next overshoot is reducing. That means slowly it will settle down and merge with the input. But as you gradually increase the damping factor, you can see that at maybe damping factor above 0.8, you see that there is no oscillation in the system. The input just gradually increases and merges with the output. So this gives you some understanding about how second-order system behave, the output of a second-order system behave with respect to time at various damping in the system. So I'm just going to change slide here. I need to stop share. Give me a moment, please. So now we take an example of a second order system, and I will take one example that is from a heat transfer thermal application. We took this example earlier also when we treated this system as first order system. Now with additional information, the problem becomes more complex where we have to treat the system as a second order system. Okay. So previously what we studied is that we had an electric bulb. Okay. And we said that the bulb is at some temperature TB and ambient is temperature TA. And the bulb is basically at some capacitance CV. And then we treated this as first order system and say that if you switch on the bulb, how quickly it will reach the steady state. Okay. We did not really talk about what happens inside the bulb. So inside the bulb, there is a filament, right? And if you consider the filament, you can bring in the filament, then you will see that this system with the filament, the bulb and ambient is no longer a first order system. You have to treat this as a second order system. So this is the thing that is studied here. So you are talking about the filament temperature at some TF, okay? And the thermal capacitance of the filament is CF, okay? So because there is some thermal capacitance, there is some thermal energy storage in the filament. And then this filament is encapsulated by this glass bulb, okay? And the bulb has a temperature of TB and thermal capacitance of CV. And outside, you have the ambient as some temperature TA, okay? So you have basically the heat exchange between the filament and the glass, the bulb surface, then the bulb and the outside world, which is the ambient. Okay, so you basically now two stages we are going to analyze this thermal problem. So essentially, you can construct a thermal model of this system. So you have the electrical energy that is coming is being converted to thermal energy in the filament. So you have heat input from the electrical heating coming to the filament surface. And the filament has, as we said, temperature of TF, the thermal capacitance of CF. And the heat now flows from the hot filament to relatively cooler the bulb surface. Okay, that is here. That bulb has a temperature of TB and the thermal capacitance of CV. And the filament and the bulb are separated by a thermal resistance that is indicated as RF, because if in a physical system, between the filament and the bulb, there will be air, right? So the air will impart some thermal resistance, which is represented as RF, the filament to bulb thermal resistance. Then you come to the bulb surface, like in the first order system, we had the bulb and the ambient, and between the bulb and ambient, you have the thermal resistance, okay, RB, okay, which is the film resistance. Now, you have QF coming from the filament to the bulb, and QB coming from the bulb to the ambient, okay? So we write down the constitutive relations. So for the thermal capacitance, we have the capacitance C times the temperature change, temperature gradient. C into dt over dt would give us the heat flux. Okay, this is the conservation of energy. Rate of change of object times the capacitance will give you the heat released or heat absorbed, right? This is the first law of thermodynamics. Now for thermal resistance, we have this relation coming from the Fourier law of heat conduction. That is, the temperature gradient is the heat flow rate times the resistance, okay? An equivalent analogy is the voltage, current, and resistance. Similarly, your temperature drop is here like the potential difference. Q is like the heat flux is like the current, and the thermal resistance is like the electrical resistance. So you have this equation. Now we write these equations specifically for the filament as well as the bulb. If we write down this for the filament, it will be CF times dTF over dt will be equal to the net heat flux. What is net heat flux? Here for the filament, Q in is coming because of the electrical heating, and QF is leaving to the ball surface. So the net is Q in minus QF. That causes the rate of change of temperature of the filament. Similarly, the capacitance of the bulb times the rate of change of temperature of the bulb will give you the net heat flux. That is, QF is coming to the bulb and QB is leaving from the bulb. So the rate of change of temperature of the bulb into thermal capacitance would be the net heat flux. So essentially, here we have two different equations. Okay. And so you can actually write QF from here. For the thermal resistance, QF you can write is a delta T over R. So which is the temperature drop across the filament is TF minus TB, and the resistance is RF. So basically QF from here, Q will be delta T over R. So QF will be delta T, which is TF minus TB divided by R is RF. Similarly, the across the bulb, the QB living here is basically TB minus TA, the temperature of the bulb minus the temperature of the ambient divided by RB. So if we combine these two equations here and these two equations here, essentially we substitute for QF from here and QB from here, we substitute there. Then we can write that CF dTF over dt, that is coming from here, CF dTF over dt equal to Q in, that is here, minus QF, and minus QF is here. This minus QF is minus 1 over RF, TF minus T. Similarly, the second equation, we can write CB dTB over dt, CB dTB over dt is QF minus QB. So QF is 1 over RF into TF minus TB, and QB is 1 over RB into TB minus T. So basically, now we have two equations, combining those four equations. So we need to now these two equations into a single second order equation, differential equation. And to do that, we need to choose a single variable to represent the system, and then write a second order ordinary differential equation using that variable. Okay. And so that way we will be able to easily solve. Now we have two different variables, so that is difficult. So let us focus on the bulb envelope temperature, which is TB. So we need to eliminate TF. Okay, so we eliminate TF and substitute here. So we only have one equation, then we have one unknown, that is TB. Okay. So that is the thing that we are going to do. And to do that, it will be helpful to introduce this operator notation. Okay. So the operator D represents differentiation. So this capital D of function ft is basically d of ft over dt, which you can also write it as f dash t. If you differentiate this function again, you get d square ft, which is basically the capital D square ft, which is d square ft over dt. Dt should be dt square. And that is equal to f double dash t. Okay. So here you write that Cf dTf over dt. From here, Cf dt over dt is basically the same thing you write here. Now, your dTf over dt is basically, your d over dt is written as capital D. And you multiply both the sides with Rf, this Rf. So you have Rf into Cf into d by dt, which is d. And then you will also have Tf here, minus Tf on the right hand side. If you take to the left hand side, it will become plus Tf. So that means Rf Cf d plus 1, the whole thing into Tf. Okay. So basically this is d by dt of Tf. This is only Tf when multiplied. So that is equal to Tb, because here it is, there's a minus sign. Here there is a minus sign, so it is equal to Tb plus you multiply the Rf both sides, so Rf into Qn. So from here, you can write that your Tf is going to be Rf Cfd plus 1 to the power minus 1, because this you are taking to this side, into Tb plus Rf into Qn. Okay. So basically, you have now found an expression for Tf in terms of all other parameters. So if you substitute this Tf in this equation here, Tf, then you have only one variable Tb. Okay, so that is exactly you do. You basically substitute this expression for Tf here. So when you do, and then you do some algebra, you just do some multiplication of Rb on both sides. So you have Rb into Cv into dTb over dt. So which is Rb into Cv into d by dt. Your Tb is here. Then you multiplied Rb, right? So this will be Rb over Rf into Tf. Okay. Then you have Rb over Rf minus Tb. So that minus Rf Rb over Rf into Tb goes to the other side, becomes plus. So that is here. And this, when you multiply Rb, becomes just Tb. So this minus 1 goes to the other side, becomes plus 1. And then you have Rb over Rf into Tf. That is plus, so goes to the other side, becomes minus. And Tf is basically this from here. Tf is basically that. So you write this, and part of this Tf, which is this term, comes to the right hand side here. And then you have Ta, minus, minus, so you have Ta. So all the terms from, just by substituting for Tf from here, you got this equation. Then you do some adjustments, okay, which I'm skipping from here. So if you just open the bracket and do the adjustment, you can see that this equation you're going to get. So Rb, Cv, Rf, Cfd square plus Rf plus Rb into Cf into D plus Rb, Cb into T plus 1 Tb is Rb Qn plus Rf, Cfd plus 1 into Tn. So now this d you write as d square by dt square. So you have Rb, Cv, Rf, Cf, d square, Tb over dt square plus RF plus RB into CF plus RBCB into dTB over dt plus TB is whatever you see on the right side. You have RB into Q in plus RF CF dTA over dt plus TA. So basically we have to solve for TB. Okay. So if you take that your ambient temperature is not changing with time, that means your ambient temperature dTA over dt is 0. And you define temperature T as TB minus TA. Okay. Then TA is not changing with time. So dt over dt is dTB over dt. D square T over dt square is d square TB over dt square. So now you can write this as d square TB over dt square. You can just write d square T over dt square. And here your dTB over dt goes to dt over dt. And TB, this TA goes to the other side minus TA. TB minus TA becomes a T. And here you have RB into Q in, which is here. And your dTA over dt is 0 because ambient temperature is not changing with time. So this term is 0. So you have basically this equation. Now, for a typical 60 watt electric bulb, the resistance RB is typically has been estimated to be 2 Kelvin per watt, and RF is like higher because it is air, so 40 Kelvin per watt. Capacitance of the bulb surface is 65 joule per degree centigrade. Capacitance of the filament is very small, 10 to the minus 3 joule per degree centigrade. Now from here, from these practically measured values, you can see that the resistance of the filament is very high compared to the bulb resistance. That means if you have a term like RF plus RB, you can just approximate this as RF, because RF is very, very high compared to RB. So you do this approximation and you say that since this is a second order system, the solution to that is of the form xt is c e to the power st. So d square x over dt square is basically s square e to the power st. So you get s square here, and you get s in the first order term dt by dt plus 1 equal to 0. So this equation becomes this when you say that your temperature, in this case it is temperature, so T as a function of time is equal to C some constant times e to the power st. So then from this equation, you can go to this equation. So now this, you can actually see that this is nothing but, you can express this as the multiplication of two terms. So you have RBCBS plus 1 into RFCA plus 1, which is basically this term, is equal to 0. Now, if you look at these practical values, your RB and CB, RF and CF, RBCB is 2 into 65 is 130. RF and CF is basically 40 into 10 to the minus 3, that is 0.04. Remember, R into C is basically like a time constant. Okay, resistance time capacitance gives you a time constant. So RB and CV, let's call it some tau B, and RF CF, let's call it some tau F. So you can see that tau B is about 130 seconds. And tau F is only 0.04 second. So notice the two widely different time constant. Okay. So the time, the long time scale, that is this tau B, 130 second, is associated with the thermal transient on the bulb envelope. the bulb surface. And it takes about 5 times time constant. So 5 times tau b comes out to be 10 minutes. Okay, for the bulb temperature to equilibrate with the ambient temperature. But there is another time scale, which is a short time scale, okay, 0.04 second, that is associated with the thermal transients of the filament. Okay, and this small piece of coiled wire heats up and cools down far more rapidly than the glass bulb envelope. And from here, we can say that it takes of the order of 5 times time constant will be only 0.2 seconds for the filament temperature to equilibrate. Okay, and that is something you actually see in daily life, right? The filament, which is red hot because of its very, very high temperature, almost instantly cools down, right, to a very low temperature because the time constant is so small that instantly cools down, and then you do not see that radiation coming from the bulb after you switch off. So it says that this fits with our experience in watching the filament temperature collapse rapidly when an incandescent bulb is turned off. So as soon as you turn off, the temperature cools down so rapidly that you don't see the glow anymore. But at the same time, if you touch the bulb surface, it remains hot for a long time because the time scale of cooling is very large. It's about 10 minutes or so. This equation is very similar to the second order equation, the generic second order equation that we talked about in the very first class when we talked about second order system, which is 1 over omega n square into s square plus 2j over omega n into s plus 1 is 0. So this is a generic second order equation. And this is similar to what we get from this thermal system. And if you bring similarity between these two, you can see that your omega n will be 1 divided by square root of this term here, which is RB, CV, RF, CF. And 2j over omega n will be RF, CF plus RB, CB. And if you use the numerical values for this example, you have RF, RB, CB, CF. You can show that this omega n is of the order of 0.44 radian per second. And J happens to be about 57. Okay. Now, in this case, if you want to see the poles of the system, so here you have the real axis, here you have the imaginary axis on a S plane, the frequency plane. And you can see that the poles are basically frequencies, and you see that tau b is 130 seconds. So your SB is minus 1 over tau b, which is minus 7.1 into 10 to the minus 3 second. And SF is basically minus 1 over tau f. Tau f is 0.04 second. So SF is about 25 per second, 25 hertz. This is about 7.7 10 to the minus 3 hertz. This is about 25 hertz. And the natural frequency of the system, which is basically the solution to this equation, is, we said that is e to the power c e to the power st. But here you have two values of s. Okay, one value of s is here, another value of s is there. So this s is basically minus 1 over tb. This is minus 1 over tau f. So you can write the solution, the simple, the natural response is basically C1 e to the power minus t over tau b plus C2 e to the power minus t over tau f. Okay, so this is how you would analyze a typical second order system, study their response in terms of the frequency and the damping coefficient. If you know the geometrical parameters and the properties of the system, and you can get a solution to the response of the system as well. So I will stop here.